Good afternoon. On behalf of Engineers Australia, I'm delighted to welcome you all to our Thought Leaders series, Convergence of Energy and Infrastructure. Firstly, in keeping with our tradition, Engineers Australia acknowledges the traditional owners of the land and recognises their continuing connection to land, waters and community. We pay our respects to their cultures and to elders past, present and emerging. Before we get started, I'd like to acknowledge that today's webinar is being hosted with our university partner, RMIT. RMIT has a reputation for excellence in work-relevant education and high-quality research. Its courses are constantly updated to meet the challenging needs of business and the broader community, and to provide students with specialised content relevant to professional and personal success in a rapidly changing world. With over 120 years of educational excellence, RMIT offers programs and courses ranging from postgraduate degrees by research to employment-focused diplomas and certificates, and offers a global passport to study internationally with education that aligns with industry-producing graduates that excel in an open world economy. I'd now like to welcome our moderator for this afternoon, Dr. Bronwyn Evans. Dr. Evans is the CEO of Engineers Australia, the Chair of Building 4.0 CRC, a Director of Standard Communications GME, and was recently the CEO of Standards Australia and Vice President Finance of the International Standards Organisation ISO, and a Director of the Australia-Japan Foundation. Bronwyn has previously held positions in innovation initiatives, including as Chair of MTP Connect, the Industry Growth Centre for Medical Technologies and Pharmaceuticals, and was a member of the Industry 4.0 Advanced Manufacturing Forum Leadership Group. Bronwyn has over 35 years' experience in various engineering roles, including Cochlear and GE Healthcare. She has an honorary doctorate from Swinburne University, is an honorary fellow of University of Wollongong and Engineers Australia, and a Fellow of the Australian Academy of Technological Sciences and Engineering. Bronwyn has been recognised as one of Australia's 100 most influential engineers and recognised in the top 100 women of influence.
Thank you very much, Amanda, and welcome again to our viewers. I'd like to welcome our keynote speaker for today, Dr. Michael Weinhold, who's the Global Head of Technology and Innovation Smart Infrastructure at Siemens. Dr. Michael Weinhold is guided by the idea of creating environments that care, because only together can we effectively master the challenges placed on us by climate change and the rapidly changing energy systems. We must therefore use our resources more sustainably and create an interconnected ecosystem encompassing energy, buildings, and industry in order to preserve our planet for future generations and prepare a better future for our society. After graduating as an electrical engineer with subsequent PhD at the Faculty of Power Generation and Applications at Ruhr University Bochum, Dr. Weinhold started his career at Siemens AG. After working as a commissioning engineer in the field of network planning and high voltage systems, he took over the position of Chief Technology Officer and was responsible for technology and development from 2004 to 2008 at Power Transmission and Distribution, until 2014 in the energy sector, and lastly in the Energy Management Division. Currently, Dr. Weinhold holds the position of Global Head of Technology and Innovation Smart Infrastructure. He heads the Technology and Innovation Department and deals with leading edge technologies in the fields of power grids, intelligent buildings, and using digitization to interconnect them. Dr. Weinholt's area of responsibility also includes data analysis and artificial intelligence, as well as power electronics and cybersecurity. Change conditions, such as the increasingly strong effects of the climate change and growing digitization, require innovative spirit and commitment going beyond daily business. This is why Dr. Weinholt was nominated Inventor of the Year in 1997 and Siemens Top Innovator in 2008. Besides, he's been active as a member of the main board of directors of the industry association Bitkom and at Acatech, the German Academy of Science and Engineering, since 2019. Please welcome Dr. Michael Weinholt.
Yes, hello, ladies and gentlemen. Thank you very much for the invitation to present here the future of energy and infrastructure. It's a great honor for me to be back in Australia again. So in my presentation, I want to talk about the trends, the ongoing trends, and then give examples, concrete examples of projects around the world which make those trends more descriptive, and I'll also give an outlook. So what is the overarching trend that I see? It's this combination of the real, the physical world, and the digital worlds. And this is very necessary in order to cope with the sustainability challenges that we have. And I will give you many examples where this combination gets very descriptive and tangible. So this is the overarching trend, and this is ongoing all around the world. I've subdivided my presentation in these three parts. So first, what are the general trends, then the concrete examples, and then I will conclude and give an outlook. So we are talking about several ongoing pushes in technology and in society. Some of those are written here on this slide. The most prominent ones that I will dig into deeper is the climate change issue and the sustainability issue. I'm very often in discussions with stakeholders around the world, like industries or academia or politicians. And these two topics, climate change and sustainability, are the most prominent one, and they always appear when discussing what is going on and what to do. So let's look a little bit deeper into the sustainability issue and the climate change issue. In order to reach sustainable environments in the energy system and our infrastructures, we have to decarbonize. And this means that we have to ramp up the renewable power generation in the electricity sector, because the electricity sector is key. It can integrate vast amounts of renewables. And then, as you know, electrical energy is very versatile in application and usually also leads to efficiency increases. For example, if you think about adjustable speed drives in industry or heat pumps for heating and cooling in our buildings. And this does not go without a decentralized setup. So we are seeing around the world more and more renewables, renewable power plants or combined heat power generation power plants embedded in our urban areas. And we also see them, of course, outside our urban areas on the countryside, as, for example, the big wind or photovoltaic power plants in Australia or in North America and other parts of the world. These trends, they are accelerating. You see here the numbers from the last, let's say, 10 years. And you see that increase in electricity consumption globally. You see that increase in renewable capacity having built up. And you see the annual renewable power generation that we already had in 2019. And that number is increasing and will increase because it is the key lever to decarbonize our infrastructures. I live in Germany. Actually, I'm running this presentation out of my home office in Germany. And just to make it more descriptive, this trend, you see what has been achieved in my home country. We had around about 20% of net electrical energy production, annual electrical energy production in Germany 10 years ago. Last year, we had already over 50%, and we have the target of more than 65% net electrical energy production in Germany by 2030. And this means that we have a paradigm shift. When in the past generation followed consumption, now due to the variable infeed of renewables, especially wind and solar, we are coping with curtailments, with redispatchments, and in the future, generation and consumption, they will sort of be decoupled, but they have to be organized. That's why we need more and more flexibility throughout the system, end-to-end flexibility from a generation through the grids into the end consumption, into the buildings. And I'll touch down on that in more detail. Looking ahead, see what we are anticipating in Germany. Germany, again, as an example, by 2035, probably will have more than 80% annual net electricity production by renewables. And this means that we have at times in areas, for example, here you see northern Germany, where a lot of offshore wind power arrives, we have a big surplus of electrical energy in that region. And in other parts where we have the big load centers and cities, we have to actually transport that energy in. So that's why electricity grids are so essential. But we will also see more and more of so-called sector couplings, meaning that we bridge over from the electricity system, which decarbonizes through the renewables, into the end applications, like you see here on this slide, like thermal usage, heating, cooling systems. Don't forget that houses, buildings are also very good energy storage elements, because the thermal time constants typically are quite high of buildings. We are seeing around the world the ramp up of electromobility. For example, battery-powered or battery-based electric cars and connected charging infrastructure, but also hydrogen powered trucks, and looking forward, trains, ships, and so on are being discussed, and pilot projects started around the world. And of course, we'll use the established storage elements that we have in our systems, like, for example, pumped hydro storage. Of course, this is a regional topic, a geographical topic. Some countries don't have this potential. So we will pull all these levers, usage of the infeed of renewables, of the variable renewables, and the end usage, which needs to be decarbonized for a sustainable future. Examples. You see here the e-car or e-bus charger portfolio that we have within Siemens, for AC chargers and DC chargers. Power ratings, as you see, for home charging, like wall boxes, 5, 11, 12, 22 kilowatt, up to, and then if you look at pantograph chargers for buses, 600 kilowatt and beyond. So this is being set up around the world. And you see it, for example, if you go along the freeways, you see more and more of such chargers along the highways. But not only cars are getting decarbonized via electromobility, also trucks. I want to point out two quite exciting projects going on in our company, together with partners. You see here on the left side, the electrification of freeways via overhead lines, DC overhead lines. And as you see on this photo, the truck takes the energy via actually, these are two pantographs, plus and minus DC. And the concept is that while the truck goes along the freeway, it takes the energy from the overhead line And when it leaves that electrified track, it either uses its built-in combustion engine or it uses a battery, for example, or other fuels. And there are already a couple of pilot projects. One is, for example, near Frankfurt Airport. So if you happen to come to Germany in the future, send me an email and I'll point out where you can see this track. On the right side, you see a project that we are running with partners, our mobility division. It will be a hydrogen prototype train and ready to run in 2023. And the concept is that you have fuel cells on the roof of the train, and it can go with the hydrogen tanks up to 1,000 kilometers. So both are examples for how you not only can decarbonize long-range trucking or trains, which have no electrification along the track, but also how you can raise the efficiency of these infrastructures. Now, electricity and flexibility, they will be key in the future system. And just want to remind what I already hinted to, we will see more and more flexibility in the conventional power generation, fast ramping, for example, also concerning fast reactive power support, black start capability. We'll see it also in the renewable power plants, maybe in conjunction also with battery storage at the sites of the renewable power plants. We will and are seeing it, of course, in the networks, in our grids, for example, with phase shifting transformers or with FACTS controllers. And we are seeing this flexibility being implemented in our buildings, for example, via controllable loads, or just think about the e-car charging infrastructure where the set points are being changed. Or think about a flexible operation of electrolyzers for green hydrogen production. So all this flexibility is happening throughout our infrastructures, and it is very much needed, again, in order to decarbonize via the variable renewables, especially wind and solar. Buildings will be deciding because major usage of energy is happening in buildings. And while we are having the flexibility being implemented in the surrounding infrastructure, the buildings themselves, they get equipped with automation technologies if they don't have it yet. And this typically raises the efficiency of at least 20% of buildings, if not more. And they will, over the next years, also have components of autonomous control and adaptive controls. So also don't forget that buildings being equipped, for example, with renewable power generation, with storage, with e-car chargers, for example, with combined heat power generation, they themselves resemble small energy systems. So in a way, what we are witnessing globally is that not only the surrounding infrastructure gets more complex and is being digitalized in order to enable the flexibility, but the same thing happens also in our buildings, in our industries. And these two, they interlink, they must interlink in order to have the already described flexibility throughout the system. And this trend is also visible if you see that we do not only have the ramp up of distributed energy systems, but also we have the ramp up of the Internet of Things, not only in industry, but also throughout our energy system and infrastructures. So those two trends, the IoT trend, the digitalization trend, and the distributed energy system trend, those go hand in hand, they merge, and in a way they also accelerate each other. And this is good because it's very much necessary to reach sustainable infrastructures. And what we are seeing, this is another, let's say, picture or inroad of looking at it. We have on the bottom, we have our real world we are living in. like the power plants, like our industries and buildings. And this gets a kind of overlaid by a digital value stream. And this value stream may be, for example, cloud-based, so having those parts of planning, operation, and maintenance. And parts of it, and maybe more and more in the future, of this digital value chain will be embedded in our infrastructures. Just think about the increased so-called edge computing capability, or distributed edge computing capability. So here again, you see this picture, this concept of the convergence of the real and the digital world. Again, very much necessary to reach our sustainability targets. Now, in the second part of my presentation, I want to give you some examples of the realization of these concepts around the world to make it more descriptive. And the first example is from Finland, where the transmission system operator, the TSO, FinGrid, implemented a digital twin, one single database of truth. And a lot of the company processes, they are actually running on this digital twin, like the planning process, the operation, and the maintenance process. And you see in the figures below that it reduces the efforts of the processes in the company. It also allows forward planning, and it improves grid reliability. You see here the value of a digital twin applied to a transmission grid. We are also implementing more and more artificial intelligence into our infrastructures, and we are using them for decision support. You see here examples of projects that we are running concerning, in this case, concerning the disturbance classification if something happens in the grids, and another example is fault location using artificial intelligence. Other example of application of neural networks or artificial intelligence is the coordination of downstream loads in a distribution grid. And this is the picture of a project we are running with the municipality of the city of Hamburg. They have more and more chargers embedded in the low voltage network, and a neural network embedded in the transformer substation. Actually gets trained in the cloud and then does a real-time state estimation, and thereby decides whether via power line carrier the downstream loads should change the set points or not. And this actually helps avoiding overload conditions in the distribution grids. So another example of digitalization applied to our real world. Again, we have more and more distributed generations, flexible loads, storages in our system, and they are being combined, for example, via so-called virtual power plants. And these combinations of dispersed flexibility actually can be brought to flexibility markets. And so it can organize generation, load, storage in a given region, and thereby also raise efficiency in that given region, or, as I pointed out, can be used to address, for example, flexibility markets like the primary control market, secondary control markets. This is also an example that we are now seeing more and more new business models arising in the digital world. And there's a lot of creativity out there, and probably a lot of the listeners to my presentations already have a lot of ideas what can be done in the future to concerning business models in order to raise even more efficiencies throughout our system. Another example where the digital world helps are, for example, microgrid management systems. And this is an example from North America. It's in a remote area. A microgrid controller helps integrating photovoltaic power plant, batteries, also integrates building automation systems, and In the past, during blackout conditions of the surrounding energy system, this village actually ran through. There was no blackout because the microgrid controller could run the electricity system even under blackout conditions of the surrounding system, and then, of course, reconnected once it was back again. So a microgrid controller does not only help coordinate generation loads and storage in a given area, but thereby also helps decreasing the carbon footprint, raising efficiencies, and by providing flexibility to the surrounding system, may even earn money on the energy markets. Another example that I want to point out is the brand new city district of Aspern in Vienna, in Austria, where, you could call it a living lab, where we are together with partners. We are investigating what can be done in the infrastructures, in the buildings, in the office buildings, for example, also in the interaction with the people in the buildings, in order to not only raise the efficiency in that district, but also to provide flexibility to the surrounding energy system. So this district is already there. It's 20,000, around about 20,000 housing units, as you see here, are being planned for 2028. Another project where you see the combination of buildings and the surrounding energy system is here again from Finland, where the biggest shopping center in Finland was not only equipped with latest automation system, but also with battery storage and solar PV on the roof, and thereby not only decreases the carbon footprint of the shopping center, but also provides flexibility to the surrounding energy system. It's integrated into a virtual power plant concept, and thereby even earns money for the operators of the shopping center. Reaching out to the people in the buildings is, of course, essential to provide comfort and safety. And these are examples of technologies that we have, sensor technologies, but also apps where the user in the building, the man or woman in the building can interact actually with a building control system and, for example, finds free space where to work or available conference rooms, and also gets information about how to best, for example, get home in the evening. So these apps are becoming more and more prominent, and they not only make our professional life more easy, more comfortable, but they also raise the efficiencies in the buildings, since people room usage can be better anticipated, and people can be better guided to areas where, for example, the conference rooms are already cooled or heated to the correct temperature. By the way, we are rolling this out around the world to our office buildings. And we are applying it. For example, in our new campus in Zug in Switzerland. That's where we have our smart infrastructure headquarter. And the headquarter building was newly built, also applying digital technologies like building information models. The people working in the building could actually visit it before via virtual and augmented reality. And as I mentioned before, the apps are available, which make the life and the work in the building more comfortable, more enjoyable. By the way, we have a target of being net carbon net zero by the year 2023 in our Zug campus. This is not only by applying renewable technologies as power intake, like photovoltaic power plants and heat pump technologies to raise efficiency of the buildings, but also via new constructions. So I would like to conclude my presentation and summarize. We are seeing decarbonization in our energy systems, in our infrastructures, more and more via direct and indirect electrification. Electrification is key. The energy grids and the buildings, they merge into one optimized system. I mentioned this end-to-end flexibility needed. Flexibility is key, since on the one hand, we have variable renewables. On the other hand, we have more applications with variable characteristics. Just think about the e-car charging infrastructure at the grid edge. In order to cope with this change, we need the digital world. So, for example, we are implementing digital twins for our industries, for our grids, for our charging infrastructures. And these digital twins, they allow more efficient data analytics, more forecasting throughout the life cycle of our infrastructures. It is very important that we need this close interaction between society, academia, and industry. This is crucial, that all these so-called three forces, that they go hand in hand, and then we will best and fastest master the transformation. And I want to congratulate Amit and Siemens in Australia to the Digital Energy Lab, because I think this is one very, very good example for this close interaction between these three key stakeholders. This will allow also the young generation, the students, to learn and maybe come up with new ideas about the energy system and the infrastructures of the future. I thank you very much for listening to me. I'm now looking forward to the statements of Alex and Jeff, and also, of course, for the discussion that we will have. Thank you very much.
Thank you very much, Dr. Weinholz. What a fascinating and inspiring session. For me, I think we've seen the future of renewable energies and transport, and it's right here and now. I'd like to welcome our panel for this afternoon, starting with Adjunct Professor Jeff Connolly, Chairman and Chief Executive Officer of the Siemens Group in the Australia Pacific region. Jeff's career in Siemens has given him direct involvement in all areas of the Siemens portfolio, as well as broad intercultural business experiences throughout Australia, Europe, and Asia. Most significantly, he's lived and worked in China for a total of 7 years. Between 2009 and 2012, he was CFO of Siemens Northeast Asia, based in Beijing and responsible for more than 80 manufacturing companies, employing approximately 40,000 people, generating a turnover of approximately 9 billion Australian dollars. Jeff has been instrumental in driving Australia's transition towards the fourth industrial revolution, Industry 4.0, the energy transition, including green hydrogen, and is an advocate for intelligent infrastructure, all supporting a sustainable future. Please welcome Adjunct Professor Jeff Connolly. And finally,
thank you.
Thank you very much, Jeff. And finally, Professor Alexander Subic, Deputy Vice-Chancellor and Vice President at RMIT Australia. Over the last 5 years, Professor Subic has led a number of Industry 4.0 strategies and initiatives nationally and internationally through his roles on the Prime Minister's Industry 4.0 Task Force, the Australian Advanced Manufacturing Council Leaders Group, as chair and co-chair on the Australian Industry Group, AI Group, Industry 4.0 committees, and as leader of the National Industry 4.0 Test Labs Network. Our panel members will come together to share their strategic vision and actions around the future of work, including the role of the recently announced Siemens RMIT Digital Energy Test Lab. If you'd like to submit a question, please do so via the chat box. Please ensure your name and also who the question is for. And we'll kick off with the following questions. So, Alex, my first question is for you. What are you doing, or what are we doing? What are we doing to prepare for the future that Michael outlined? Do you think the education sector is set up for this, and what else needs to be done?
Hello, Bronwyn, and thank you for your kind introduction. It's a pleasure to be part of this panel discussion, and I'd like to thank Michael for his insightful presentation. And that's where I might actually start with my response to your question, Bronwyn. We've seen from Michael's presentation that decarbonization, decentralization, and digitalization are playing a critical role in the energy sector, or the power supply sector, if we want to coin it that way. In fact, digitalization is the core enabler for decarbonization and decentralization of power infrastructure. And that has come out strongly from Michael's presentation. If we dig deeper into that area, we've seen from his presentation, but also from our experience with the Industry 4.0 transformations in Australia, as you've pointed out in your opening remarks, Bronwyn, that the broader industry sector, energy sector, is starting to implement in their operations the same emerging technologies that are driving the fourth industrial revolution in the manufacturing sector as well. So we've seen the industrial Internet of Things, machine learning and AI, cloud computing, edge computing, and similar new technologies that are already being used by several power utilities around the globe. And in fact, we are seeing now those technologies entering the Australian energy sector. And indeed, over the last 5 years, as you've pointed out, Bronwyn, we've been leading that transformation along the Industry 4.0 agenda in the manufacturing sector. So we are seeing the same trend now entering the infrastructure and energy sector as well. What have we been doing in order to support that transformation? I think that we are positioned well in Australia now to embrace this change based on the learning and based on the transformation we've been leading and we've been experiencing in the manufacturing sector in particular over the last 5 or 6 years through the Industry 4.0 strategy. We now have across the country Industry 4.0 test labs. We have hubs and clusters which are engaging universities and industries along that journey of transformation, utilizing the technologies I've mentioned. The test lab that you've announced, Bronwyn, the Digital Energy Test Lab that Siemens and RMIT have established recently on RMIT campus in Melbourne, is in fact an example of how we are preparing for that transformation. It's about readiness, developing our readiness collectively for that transformation across the energy sector. I'll say perhaps a bit more about that lab later, but that's exactly the type of infrastructure and the type of environment that will help our stakeholders, industry, universities transform and prepare better for that energy 4.0, if I can call it that way, new era in the energy sector domain. It allows us to collectively learn by doing. It allows us to develop digital twins of smart grids and more complex systems that Michael was talking about, that are far more complex than what we've seen in the past. And in fact, our current grids are not ready for that transition. And this is why this immersion in new technologies and our collective engagement on this transformation is so essential. Thank you, Robin.
Thanks, Alex. Thank you. I really appreciated your comment around digitization and the decarbonisation and decentralisation and the role the test labs have. And Jeff, I've got a question for you. You made a series of significant software grants to universities and you've personally got a very significant role in the commercialisation of research. What changes are you trying to achieve, and how will that support the future that was so carefully and brilliantly outlined by Michael this afternoon?
Yeah, thank you, Bronwyn, and thanks to Engineers Australia and RMIT for hosting today. I think, if nothing else, all the engineers online would have been inspired by what the future holds for them as a consequence of what's currently happening in the environment. If the catch cry, decarbonisation, decentralisation, flexibility, but actually it's all enabled by digitalisation at the end of the day. So it sort of strikes a chord, and that's my introductory remarks, that there is a close connection here in the needs of getting prepared for the future and the work we did on Industry 4.0. Just as a recap, that whole terminology, Fourth Industrial Revolution, was coined by the Germans at least 8 years ago. And it wasn't a marketing slogan. It was just simply foreseeing this massive societal transformation as a consequence of this capability of real-time digital enablement. So it commenced in manufacturing, but as Michael just pointed out, and we see it around other parts of the Siemens portfolio, it's relevant application in process industries, energy, healthcare, infrastructure. The Industry 4.0 framework view of what's happening to society described the future state of the cyber-physical world, and that's this unprecedented simulation, cross-discipline, digital twin, predictive capability, and real-time correction across domains, if you talk about infrastructure. And I just as an aside there, by the way, I've been asked more recently, Bronwyn, because now we have 5G, does that mean Industry 4.0 is out of date? Well, of course, the answer to that is no, because Industry 4.0 was talking already about the enablement that was foreseen by ever-increasing capability to collect data and interpret it and feed it back into systems real time. So sorry, guys, if you want a rebadging, I think let's stick with Industry 4.0 because it does describe where things are foreseen still out in the future. A couple of things also became clear with that Industry 4.0. It uses the words revolution, and I think many people thought that was about fear-mongering, Bronwyn, but actually it's about this urgent call for action on a holistic sort of way. You, Bronwyn, and I think that's not been mentioned, that two of the most substantial contributions to the Prime Minister's Industry 4.0 task force actually came from you yourself in your role as in the standards work stream, and what Alex was doing in preparing those future skills for the digital world of the future. The Industry 4.0 framework is not different to what we're talking about, what we have to get ready about in the energy sector. What are the standards we're going to have to operate in? What and how will we research? If that's all going to work, of course, we need to understand the cyber security consequences and learn how to manage that well, risk manage it, legal frameworks of trade change, and of course, as been alluded to, education. And that's where, coming back to your question, we decided that what we would do is ask the questions, is the style, content, and the quantity of education output still fit for purpose if you can foresee this cyber-physical world? Is the way we've been educating, the course contents and the credentials, are they all relevant for that future world? Ask yourself the other question, which profession will end up needing to lead that change and meet those challenges? And you can't go past the engineering fraternity. They really will need to step up and have a higher voice in the country to take the conversation away from describing problem to fixing problem, as engineers do. So yes, we decided to give software grants to one university per state to pick up a key theme, and those software grants were really just the basis of designing curriculum and the basis of actually building test labs around the nation, one in each state to start with as pilots, but operating on the sorts of sophisticated engineering, design, simulation, collaboration tools are the same ones that the leading edge engineering community are using at NASA, in aerospace, in defence, and get that into the education system so people can actually start to see what actually we're talking about. So education on the software with the curriculum, researching on that same software, and then coming around in a test lab environment and bringing industry in. So a form of triple helix in the education sector to get industry coming in and saying, aha, that's what you mean. And that concept of seeing as believing might sound counterintuitive in a digital world, but actually it has resonated very, very well. And the work that Alex Subik did there, together with Andrew Detmar, who is a very, very prominent spokesperson for organised labour, as the president of the AMWU. If you're talking about a revolution and jobs changing, then you better make sure organised labour is with you and understands where the future is and are participating. And I have to say, we had tremendous cooperation from the AMWU as we were sorting through changes in curriculum and getting that articulated. So if I now talk briefly, and you mentioned that I've got a role at the moment trying to devise a scheme with a really prominent, powerful panel on how to translate university research into something commercialisable, and we fully acknowledge that not all fundamental research has the purpose of being commercialised. But that can be, how do you steer certain types of research into use-intended research or pure pride research to get a bigger hit rate in the money that's being invested there. So not by any means criticism of what's happening in the university sector, but really utilising the researchers we've got to produce something more powerful in terms of economic transition and jobs for the nation. So they're my opening remarks, probably.
Look, thank you very much. Thank you. And you're absolutely right. It would be, I think, impossible for anyone on this session this afternoon not to have been inspired by Michael's presentation and just that massive societal transformation. And when we're at Engineers Australia, we talk about our purposes as a profession is to advance society through great engineering. And I think those test labs, I sometimes think I want to come back and be an engineering student all over again, just to work in that sort of environment. So thank you so very much. And Michael, I'd like to you now, with your global view, is there anywhere in the world that has a combined view of energy and infrastructure together when it comes to, say, policy or decision making, and which countries or cities are the most advanced in your view?
Yeah, thank you very much, Bronwyn, for this question. Actually, not an easy one, because this topic of convergence of energy and infrastructure, this is a topic around the world. And as you know, every region has its own history, has its own, for example, power plant setup, grid setup, and infrastructure. So we would actually have to look into the certain, let's say, environment, into the certain region and what they are doing. And I think this is what we are witnessing. It's the sharing of projects, of insights around the world in order to together collectively push forward. Just as an example, I mentioned the city of Aspen, close to Vienna. This is a showcase project, and this, for example, we discuss with other partners around the world and discuss what they can take out of it. Or I want to point out what we are doing in Berlin. We are building a whole new city district where people will live, work, and also spend their spare time. Here also we strive for net carbon zero and for the interaction of that district with the surrounding city environment. So again, what we are doing there, we are also sharing around the world. So maybe some countries which are very advanced with digitalization, like Finland, they are in a way also advanced in applying concepts like virtual power plants, for example. I mentioned the shopping center, and also applying digital twin technologies across their infrastructures. But again, it would be a little bit unfair to say this country or that region is front runner, as it is happening around the world, and as each of the region has its history and its own targets.
Well, thank you very much. And that's actually good news for all of us who are engineers, that this is happening to a greater or lesser extent everywhere. Which, Alex, it brings me to the point about, what about practicing engineers who've already graduated? What role should they and can they play to build the right skill sets? What's available to us who are already graduated and are so excited we want to join in on this work?
That's a pretty good point, Broman, because obviously any transformation, industrial transformation or energy sector transformation is all about people and our professionals and experts driving and enabling that transformation. Before I answer the question of maybe how that reskilling, upskilling, and currency can be maintained in the evolving kind of education and training ecosystem, I might just, if you allow me, Broman, maybe emphasize just a couple of points why this is so important, in particular in this context. If I go back to Michael's presentation and dig deep also in what's happening right now with the transformation of the sector, we've seen that with digitalization of the energy sector and decentralization and decarbonization, we are dealing with increasingly complex systems. And just to emphasize some of those complexities, there are multiple energy sources, renewable energy sources that are being developed and that are being introduced to the grid. And Michael mentioned wind, solar, gas, hydrogen, and so on. There are increasing number of devices, sensors, introduced in the network. While a number of years ago we might have looked at hundreds of devices. Going into the future, we're looking at networks that need to integrate via industrial Internet of Things platforms thousands to millions of devices that in the past have not even existed. We're looking at cybersecurity challenges and the need to build cybersecurity in such networks and systems by design from the outset and managing those. We're looking at, going into the future, remotely operable power plants and systems, as Michael mentioned, or autonomous systems on the back of this. We're looking at artificial intelligence, edge computing. These are technologies that are fundamentally transforming the nature of work and the nature of our professions. This, to be able to master these new technologies and practices, and to be able to stay current and refresh the way we work in this new, brave new world, we have to enable our professionals, our workforce, to transform with these technologies in real time, and based on that new skill, new knowledge, to implement that in their businesses and their daily practice. Going back to campus and going back to traditional education, that's not possible. So what we are seeing is that lifelong learning is becoming the core, is at the center of all these transformations, because lifelong learning is what will enable the workforce to transform at scale and pace. And this is what Jeff was mentioning in terms of the work I've been doing together with Andrew Detmar and the union and the Australian Industry Group, developing new models, new schemes, new ways of connecting the ecosystem to enable that upskilling, reskilling to happen at scale and pace in a seemingly, connected manner where there aren't barriers to entry and barriers to accessing this knowledge. The test labs were one of those ways, because the test labs are there not just for current students, but they are there in a supportive way, a non-competitive way for existing workforce, SMEs, as well as larger companies, to expose their workforce to new technologies and new ways of working. Why the test labs are so exciting, and the digital energy test lab that we've launched with Siemens for this purpose, is that those test labs emulate a work environment where we are creating multidimensional, multifunctional, multidiscipline teams involving, staff, workers, professionals from the, let's say, from the energy sector. We're involving our staff, researchers, current students around projects that are using current industry standard technologies and software that is being used by the utility sector. They're working on projects together to solve problems, to model grids, to utilize new practices and new standards, to simulate cyber attacks, to simulate through using digital twins, faults, asset management, maintenance, protocols, to optimize multi-directional energy flows, and look at those challenges that are happening, and all those practical challenges that otherwise they would not be able to embark on in their everyday practice. We're also looking at, with the support of federal government, rolling out pilots, short courses, undergraduate certificates and postgraduate certificates across the workforce through microcreds and through digital assets to enable easy access, seamless access to new knowledge and practices in bite sizes, realizing that it is difficult to balance the workload between day-to-day work in industry and studying and acquiring new knowledge and skills outside of industry, and trying to embed that new knowledge within project-based environment, work integrated learning environment, utilizing real practice-based challenges and projects that would encounter in their environments. Those are some of the strategies that we are using, and the challenge is always to move from pilots to scale, to do this at scale and at pace, because transformation of this magnitude requires larger scale workforce transformation. So that's pretty much it. From my perspective, what is required to make this even more successful is that we connect our ecosystem better, that employers, as my friend Andrew Detmer and Jeff alluded, are supportive of their ongoing, learning, upskilling, reskilling of their staff, and that our engineers and our professionals in industry, take that advantage, take the opportunity to really transform with the technological transformation we are seeing, because this is something that is happening. The dynamics of change are rapid. Today, as I always say, you would know, Bronwyn, technological change doesn't happen on a kind of a annual or decadal basis. It happens almost monthly, weekly, and this is the nature of the beast we're dealing with.
Thank you. Thanks, Alex. And it just got me thinking, and for all 1,000 of you listening live and the many thousands who listen later, this is our opportunity, lifelong learning. Let's take this call to action and do something so we can then try it on the job. As Alex said, we need to do this at pace and at scale. And it's not just Alex, Jeff, Michael, me, it's all of us. We have to do that. And Jeff, I've got a question for you that's come through, and let me say thank you to everyone who's posting those live questions. And it really links one of the comments that Michael made about this is happening all around the world. And the question is from Hilton, and his question is, will Siemens market its products and technology applications to encourage state governments in Australia to meet renewables targets?
The simple answer to that is yes, of course. I think we see the adoption of technologies. What we're doing today is explaining that future, and people need to decide how they best apply technologies. The state governments are where they see gaps, they're taking up the initiatives themselves according to what their priorities are. The federal government, there were some commentaries about, I think in the last 24 hours, the introduction of capacity payments just to organise the transition in energy. I I could almost hear the noise on. Well, of course, all you're doing is prolonging fossil fuels. I have to say, Bronwyn, I don't know if anybody listening actually has had the pleasure of listening to any of Alan Finkel's quarterly essays. He posts them on a blog, and he actually is a master of saying things in a very straightforward way, cut through, without using a lot of words. And he was talking about the net zero 2050. And behind that stands 400 milestones that have to get done to get us to 2050 net zero. He said, look, we can't switch off fossil overnight. We've got to have an orderly transition because we as a civilization need energy. So there is these pathways, and he, even in his hydrogen program blueprint, talked about different pathways to get ultimately where we've got to go, and it's to do with keeping civilizations running. So he talked also about, for the very first time, we built on, we had wood-fired energy. If you think about cutting forests and burning, we had coal. Then we built on that because we needed more energy. We developed oil technologies, and we developed natural gas technologies, just to satisfy the ever-increasing demand of the world population for energy. And then at this particular inflection point, what we're actually doing is putting new technologies into the market to solve the problems of the old technologies. So really a replacement of old technologies. And that is a one-time opportunity to really shift the dialogue. Rather than bunkering down about the type of fuel in energy generation, the new technologies will make the old ones obsolete anyway over time, and we need to keep introducing the new technologies, and keep telling thought leaders, governments, potential developers of projects to do that. Hydrogen has been started, has been stimulated. We need it on scale. We don't need more pilots there. I think we might get stuck in pilot purgatory because the base technologies are there. The final technologies that will get us to the end point in 2050 probably haven't even been developed yet. But certainly the current technologies are the ones we're going to need to get it started out to 2030. So very exciting times, probably.
Oh, look, thank you so much. And, as I listen to you speak, I really start to feel quite hopeful that we can use these new technologies to solve the, if you like, the issues of the old technologies. And I'm going to still phrase pilot purgatory. That's what we need to avoid. So thank you very much. And Michael, I think this next question, which is from John, starts to link this together. And John's question is, given your responsibility also for artificial intelligence at Siemens and the complexity you described about how important AI will be, do you already see it playing a role in the convergence of energy and infrastructure?
A very good question. Yes, artificial intelligence is already being applied, for example, in the controls of power plants. And why is that? Because the situation, for example, that a gas turbine has to run in is getting more complex, and there has to be very fast decision making how to optimally tune the controllers. And here humans cannot do the job as good as with decision support from artificial intelligence. So we have it in power plants. I showed examples from using artificial intelligence in the grids, but also we are prototyping it in buildings, for example, in controllers, automation systems for buildings. We are also utilizing artificial intelligence in quality control in industry. Everywhere where a situation is very complex and fast decision making has to be done, that's the field of artificial intelligence. Not to forget, for example, also natural language processing, which helps then to derive insights from reports of commissioning engineers, as an example. So it's there, it is being applied, and it will be applied more and more in the future, which of course then also leads to discussions about what will be the role of human beings in the future. as we are running more and more of our systems based on data analytics and artificial intelligence.
Thank you very much. And perhaps this next question neatly relates to that, and it's from Paul. So if we think about the role of human beings, maybe it could actually be malign. So Paul asks the question about cybersecurity and disruption of national services by hackers. What do you think is the risk of that, and how can we protect against that through, with this sort of mass interconnectivity?
Yeah.
Michael, if you could consider that.
Yeah, so maybe I had been in several discussions about this topic of role of human beings, and the human being will always be there to have the final say and also to step in if something goes wrong, if the analytics are not good enough. So so human beings will always be, let's say, at the steering wheel of it. Now, concerning cybersecurity, of course, this is an ongoing issue. It's like a rat race, and just to give you an idea, more than half of the colleagues in my technology and innovation department are cybersecurity experts. So just to point out the extent of how important it is that we take it, and therefore it's always about securing IT security, information process security. It's about also securing the operation of factories, for example, of running infrastructures. And it's, of course, also about product security. And all these aspects are very high, not only on our radar screen, but also on the radar screen of our customers. And since it is so high on the radar screen, I'm convinced that we will cope with it and master that challenge also.
Oh, thank you very much. And Jeff, there's a lot of questions about on the chat, but one from Ramesh is, who pays for this technology and infrastructure, and ultimately will it deliver reduced energy costs to the public?
You have to have somebody who doesn't unmute once in the call, I suppose. Thanks, Bronwyn. Look, I think it's who pays. There's got to be a business model for everything to get stimulated. Those that don't yet have a business model, there needs to be some sort of difference payment, and that's a question of how much society actually demands that, and that's sort of the gap, if you like, that I was referring to in hydrogen. So the question is then, how do we articulate the need in a strong enough way to get that subsidy going, to get us out of the pilot situation? Do you mind, Bronwyn, I just go back to a comment Michael made, and he made it in a trip previously, and it's sort of related to the question. Most power electronics in our networks were put down at a time where people didn't actually think about the need to upgrade the software, didn't think about the ability for somebody to remotely get into those devices. So the question at a board level is very often, well, what do I get if I just take all of those devices down and put new ones up there? Well, you don't get anything more. So the question is, how big a risk are you willing to take? And that, I think, my personal opinion is that needs to be done at a higher level above the individual firm level. An individual firm might say, well, good, I insure it, and therefore I don't have a financial risk, which is not really a society answer, because every single firm gets attacked at the same time in all different domains, and we have a different problem. So I think that dialogue is rightly, I think, Ramesh, you probably were referring to that. We have to lift that dialogue up and understand the key infrastructure can't be left to individual companies to make that decision. It needs to be mandated.
Thank you very much. And I have another question from Ramesh. And Alex, this one's for you. Really like your thoughts on engineers being multidisciplinary engineers, or even working with multidisciplinary teams. They're planners, environmentalists. So could we see a time where an engineer has to have that broad specialisation rather than a very narrow one to converge renewable energy with infrastructure?
That is definitely absolutely a critical question right at this particular time, and we're already seeing not only that dialogue emerging, but also new developments in curriculum architecture that are creating ways to integrate, that interdisciplinary content, and with minors and majors in engineering programs as well as in other programs. We are exploring that area right now. It is very clear, not just from the presentations today, but also from our work, on Industry 4.0 agenda and our work with industry, as well as through reports and surveys, that interdisciplinarity is becoming a critical requirement in industry in order for engineers and professionals in general to tackle these challenges, in order for them to lead change, in order for them to manage change successfully. So that needs to go beyond the models we've explored in the past, where we saw engineers do double degrees. We saw engineers in their degrees take up electives from relevant interdisciplinary areas. We saw them even work, occasionally on capstone projects with other teams. This has to be a more fundamental change, and a change where these are not just add-ons, but where we are forming interdisciplinary teams with professionals from various areas, where we are creating project-based learning that brings that content, brings that exposure to those challenges in an integrated manner, that has placements involving teams of students in industry, co-supervised by professionals that are working on interdisciplinary problems in interdisciplinary settings. And also, as you quite rightly ask, it might involve evolution of new engineering degree programs that are multidisciplinary, that are, dare I say, interdisciplinary as well. Because even in this context, if we look at just the energy and infrastructure context, we are seeing professionals, let's say in utility industry, energy sector industry, evolving as system integrators, as professionals who are mindful of and across sustainability agenda targets and policies, as well as who are able to handle multi-stakeholder issues across varied sectors and not just your traditional engineering sectors. These are very complex and mixed, sometimes even contradictory requirements that require a real academic rigor in terms of how you develop the graduate outcomes and skills to handle this. So a quick answer, absolutely. This is right now, I would say, a critical question, a critical agenda that needs to be handled, collectively as we hopefully evolve further the engineering profession.
Oh, thank you, Alex. And again, I'm going to call out to everyone on the audience. Find those 6-year-old girls and boys and tell them what an exciting future is available to them. And they can be any sort of engineer, multidisciplinary, interdisciplinary, and really changing the world. So I just can't think of a more exciting career for anyone. And
I agree,
Michael, there's
Roland.
another question.
Again.
Exactly. I think we all will. That's my my next life. I'm coming back as an engineer again. Michael, I've got a question from Jeff, and it's about DC distribution. I know at the IEC, the International Electrotechnical Commission, we were doing quite a bit of work around DC distribution. But Jeff asks, is it feasible to move away from AC and move to DC distribution? And what might be some of the implications of that?
Yeah, this is a very, very good question, a very up-to-date question. By the way, the electrification of this planet started with DC, as you know, in the late 19th century. Why did we go to AC? Because it was, at those days, we didn't have power electronics. and via AC you can transform voltages or energy up to very high voltage levels and transmit them with very low losses across huge distances. Now with the available power electronics, we can also do this with DC. The big question that we have to answer now as an engineering community is, where can DC be better applied than AC? For example, could be in certain industrial processes. For example, if you have a factory with a lot of photovoltaics on the roof, with battery storage, maybe with robots that where you have to recuperate energy, maybe there in the future it could be more efficient to run this certain part of the factory with DC instead of the established AC. But this is not an easy question to answer. I've been involved in several studies and discussions also with industry partners on that topic. So it's not. I cannot give you a clear answer by now. I can only say we look at it very closely. We analyze the scenarios. We are very active in standardization committees from IEC, for example, to prepare the standards such that DC systems, for example, in industrial applications can be applied. By the way, we do have DC already in distribution. For example, if you have railway systems, subway systems that typically run on DC. We have them even, as you also know, in very high voltage systems running HVDC lines. Also, there is an ongoing debate whether interconnected DC grids may have advantage with respect to AC. So it's an ongoing discussion, maybe in discussion nowadays fueled or incentivized by the available power electronics and digitalization technologies, and also by the increased in-feed via photovoltaics, for example, which by its nature produces DC energy.
Oh, thank you. Thank you very much. And I think that gives us a nice example then to move to the next question, which again, Michael, is for you. And this question also comes from Hilton. And the question is, could you give some examples of digital twins, perhaps industrial applications? I think you get a nice one in your presentation around the energy system and that we saw there, but perhaps there's some other examples of digital twins you'd like to share.
Yeah, the example I gave was a digital twin of a very large transmission system. Now we are also running digital twins for when we do product development, because it's somewhat easier and more cost efficient to do the development with a digital representation of what you develop, what you intend to develop, instead of building prototypes. So it shortcuts the development process, which, by the way, is also a sign of faster changes that we are undergoing also in innovation. Digital twins also being established for other infrastructures like buildings and also distribution grids, charging infrastructure, and so on. So what we are witnessing is this establishment of, I could say, digital companions also, or digital twins of parts of our energy system and infrastructures, which may get even more connected in the future. Now, what's the advantage? As I said, you can shortcut the planning, the design phase. You can also, while you're operating it, you can more easily detect faults, for example, and initiate maintenance tasks. You can also do easier forecasting. And, for example, if you have a building and you want to investigate what else can I do with the building, you just do it with a digital twin. So again, we will see more and more digital twins being applied throughout in our infrastructures, in our energy system.
Oh, thank you. And this one is sort of a one around public policy. So, Jeff, just because of the roles that you've had, I might ask you perhaps to address it. And the question from Ramesh is, who pays for this technology and infrastructure? And I think we've actually already talked about the energy costs. So sorry, I've doubled up on my questions. But stay with me, because Jeff, I do have a question more around how we address the whole debate around renewables versus fossil fuels. The future surely is more complex than slogans. So how should we be having this public debate, if you like? And you mentioned Alan Finkel's roadmap with 400 milestones. What should be our approach to talking about our roadmap to net zero?
Yeah, thank you, Bronwyn. I think earlier this week we launched with the Australian Council of Engineering Deans a new, if you like, roadmap for the way they educate. But in amongst that conversation, we were talking about the engineering community being more prominent in discussions. If you cast your mind back, South Australia had probably the highest penetration of wind energy of any of the states 4 or 5 years ago. There was a storm. Transmission lines that were designed, the engineer design life at 50 years. We ended up having a once in 100-year storm event and no power. So the consequence of all that debate that took place after that event was, to my observation, almost without an engineering content. It was politicized. It wasn't, nobody talked really about, well, what happened there in terms of what do we learn in terms of the rate of development of the renewable technologies. And it's what I tried to say before, that unfortunately the debate in Australia about net zero and doing something about the climate concerns has focused on the type of power generation. And it's important, but it's not the whole discussion. So how do you get a much more holistic view? And that's why I think the International Energy Agency, with their 400 milestones to 2050, have described that there is much more to it. And guess what? It's mainly dominated by the introduction of technologies, and it should really be dominated by engineers in the sense that you want to avoid implementing things and having unintended consequences. I might also say that in the world, and our comms here did a little bit of research, in the world currently, the most prominent engineer who leads a country is actually Angela Merkel. And it won't come as a surprise to anybody that the Germans certainly hold their engineers in very, very high regard. Look at the likes of Michael Weinheit. You won't find anybody. He's not trying to sell you anything right now. He's talking about the engineering challenge. And this, for me, Bronwyn, the issue is activism is fine because they've stimulated discussion, but actually at some point, you have to let that be a roadmap that takes into account there are different pathways, and every country will be able to swallow change at a different pace. But we need to keep talking about it. And again, I would only say that that's largely the challenge for you and Engineers Australia, is to be more prominent in your voice about the how to get things done, not what the problem is.
Oh, thank you very much. And Alex, I'd like to continue with this whole approach to engineering and engineering education in particular. For you, what are going to be the important new capabilities that you would want graduates to be developing in their engineering education careers in the next 4 to 5 to 10 years to be ready for this interconnected world of Industry 4.0 and cyber physical systems?
I think that's a critical question, and I think that's at the core. I think that question is at the core of what our engineering education should look like in order to achieve exactly what Jeff was saying, in order to enable the engineering professionals to actually lead the agenda, to lead the transformation, and to be asked what that agenda and strategy should be, to have the seat at the table. Clearly, digitalization transcends all engineering disciplines, whether we're talking about infrastructure, civil, energy, mechanical, electrical, whatever. Digital twin technology doesn't belong in any single discipline of engineering. It transcends all engineering disciplines. Digitalization capability, which is far more sophisticated and advanced than what we needed in the past, transcends all engineering disciplines. So digitalization capability, skill level, irrespective of what the level of education and training is, we're talking about skills. Digitalization skills will be critical at a far higher level. And let's start with a digital twin capability, an ability to design, develop, manage a digital twin that is actually a fusion of cyber physical, that actually is integrated with Internet of Things platforms, that is actually feeding data and keeping the digital twin relevant, current. That's the difference between modeling simulation of the past and digital twins of today and the future. That transcends all the disciplines. It's an example of sophisticated digital skills that all disciplines will have. And in addition to digitalization, apologies, what we're also seeing is that engineers of the future, and in fact, any professional of the future that wants to lead the agenda, will have to have a far higher level of cognitive skills. My colleague Andrew Detmar likes to call them cognitive skills. We in media see often is coined as soft skills. They're actually hard skills, not soft skills. They are hard cognitive skills, and that's being able to visualize systems, design systems, solve complex problems, real complex problems that have significant systems implications and multiple inputs and multiple stakeholder engagements. Working in transdisciplinary teams at various geographical locations, utilizing digital means to actually work effectively across teams, often through distributed geographical locations that are global, not just local. Communicating in ways across those multi-functions and multi-teams in ways that we haven't used technologies before. Employing augmented reality, virtual reality, online web-based communication tools in ways we've never done before, because that's how teams across global geographical locations work. Preparing value propositions and position papers and thought leadership papers within their domains of expertise, and trying to make an impact in a way that is going to position engineering solutions in a way that are understandable by other stakeholders and are providing a compelling value proposition that will get buy-in and support. All of these complex capabilities are something that we used to take for granted, or something that you develop through work when you leave universities. This is something that has to be integral to our education and training. And ways to achieve that will not be traditional, conventional ways. And all of that needs to be grounded in a far deeper, more comprehensive partnership between public and private sector, between university, industry, and business, where industry and business becomes a far more active stakeholder in that education and training process. This is critical. And that is actually at the heart of that transformation in education and training.
Thank you so much. And what a fantastic session. When I look at the questions, we could keep going, but it is time to wrap up. And look, please join me in thanking Dr. Michael Weinhold, Adjunct Professor Jeff Connolly, and Professor Alex Subic for their time and insights today. And I'm sure, like me, you learned so much. I'd particularly like to thank Engineers Australia industry partner RMIT University for making our webinar possible. We'd appreciate your feedback on the program today to help us improve and plan future sessions. Please complete a short feedback form, which is linked in the description box below. Thank you again for joining us, and I hope to see you at the next webinar. And I'm sure, like me, this was one of the highlights of the day, if not the week. Thank you so much.